Okay, welcome to Chemistry 1411, Chapter 4, Part 5. And I'm going to go ahead and start by working out this problem right here. So I'm making up this video because the actual video I recorded, I have no idea where it is. I cannot find it. Okay, let me get straight to the question. Hydrogen may replace gasoline as the fuel in the future. Most major automobile companies are developing vehicles that run on hydrogen. These cars are environmentally friendly because their only emission is water vapor. One way to obtain hydrogen for fuel is to use emission-free source such as wind power to form elemental hydrogen from water. So the goal here is to go from water to elementary hydrogen. So we have all this backstory, right? But bottom line here is water going to elemental hydrogen. So you can see the whole and part relationship, right? Water will be your whole, and then the part will be hydrogen. And they say here elemental hydrogen to make a point. It's not molecular hydrogen. So our goal here is then to go from the amount of water, whatever is given to us. Or we're given here a gallon of water. So let me go ahead and write here. We're given 1 gallon. Okay, I was a little presumptuous here. We're given, 1 gallon of water. This is going to be our whole, right? And they're asking here what mass of elemental hydrogen, and what is wanted is grams of elemental hydrogen, okay? And this is going to be one of our givens. So we have that, and we're also given the other given. These are all the givens. So the givens are on the left, the wanted is on the right. We're trying to solve for the grams of hydrogen. The other given is going to be 1 gram. Okay, these are all 1.00. I don't know why the me today is leaving out these 0.00s. Yeah, they're 3 sig figs, right? 1 gram per milliliter of water. This is the density of water, right? Once again, the water here is whole. Okay, so our goal is then to go from a part to whole relationship. Now, I can just presume right now, we might actually need a part to whole. Since our goal is to get the grams of hydrogen, at some point we might use the mass of water to mass of hydrogen. I don't know, it might be moles. Let's see how it plays out. Since we have these given numbers, our goal is then to start with a given number, and then at some point see how we cross over from the whole to the part, right? Because the given numbers are both whole information. So I'm going to start with the simplest number as usual, 1.00. I'll write this as gallons of water. This is the given number and the given unit. I'm starting with the simplest one, so I pretty much started with this part here. Now, remember the gallon is a volume, right? And let me go ahead and rewrite this right here as the fraction, so y'all can see how I use that 1.00 grams per milliliter as a fraction when I come to it. I will write it as 1.00 grams of water, right? Because the chemical referred to here, the density is water, and that will go with 1 milliliter of water, okay? So this is writing this as a proper fraction. Okay, what else do I need? So the gallon is the volume, right? The grams is the mass. And over here, this is a volume also. Since I have a volume and a volume here, I need to reconcile these volumes. So one way I can do that is with a conversion sheet. So let me find a conversion sheet that converts gallon of water, which I have right here, into milliliters of water, okay? Because we need to get rid of gallons of water. That's not in our answer. And we need to somehow incorporate milliliters of water. So what I'm going to do here is I'm going to scoot this over. I have a conversion sheet here. Let me go to the volume section. So scroll down. I need the gallon part. Okay, so I'm scrolling over. I see a gallon right here. Oh, gallon. I got 1 gallon, 3.785 liters. I'm going to go ahead and use that. 1 gallon. Of course, my chemical here is water. Okay, this is when I'm running out of room, right? Let me move this to the side. 1 gallon of water, H2O, and that goes with 3.785 liters of water. Okay, so remember I'm using this part right here, right? I'm using, can I draw on here? I'm using this conversion here. Okay, if I use that conversion, it cancels out gallons of water, but now I am at liters of water. Now, for me to use this conversion, which I can replace this with that, I need to have milliliters of water. I'm at liters. So I'm going to use the other conversion, liters to milliliters, this one here. Not the middle part here, just this and this. I'm going to use that part next. Okay. I think that might give me what I want. So let me scoot this on the side. So I'm going to have here 1 liter of water goes with 1,000 milliliters of water. Okay. And so we got liters of water, milliliters of water. That works out. Our next move is then to use this conversion. Now I can use this conversion here because you all see this conversion has milliliters of water. I'm going to use it as is and put the 1 milliliter of water here as a volume. And then I'm going to put the 1.00 grams of water. And this is, of course, our mass. So when I work this out, for right now, since I'm running out of room, you know what? I just remembered, guys. I just remembered. I can make this smaller, you know? Oops. Okay, that's when I got too excited and I moved too quick. Oh, there's a new way of moving. You know, I'm the kind of person who doesn't like updates and features. I wish they could update it without changing the function, like make it better without changing a lot of stuff. I'm just lazy. Because when they update stuff, I feel like I have to learn like 10 new skills just to use the same equipment I could use before, right? Okay. So what I can do here now, I like that. Let me go ahead and erase this and then write a little smaller so I can actually fit the rest of the conversion right here. Okay. So this is what I have so far. You can see how this cancels out, right? So the progress I've made so far, I've used the first number, I've used the second number. Now I have to find a relationship because if I stop right here, what I have is grams of water, right? But they want grams of hydrogen element. So this, remember, is the mass of whole, mass right here, whole. We want the mass part. So we have to bring in the part. I'm going to relate the whole to the part so we can see how it relates, right? So the whole compound is water, the molecule. Water, the molecule, has got 2 hydrogens. So water goes with 2 hydrogens. There is 2 hydrogen atoms, right, in the one water molecule. Since we're dealing with mass of water right now, our options are we can use a mole-to-mole relationship or a mass-to-mass relationship. I'm going to go ahead and go straight for the mass-to-mass relationship, y'all. So let's find the water's mass, right? H2O is essentially 2 hydrogens and 1 oxygen. Maybe I could write this in the bottom. You know what? Let me do that because I feel like I'm just kind of cramming everything up here. So we're saying once again, in one amount of water, we have 2 hydrogens, right? So the mass of water is going to be 2 hydrogens plus 1 oxygen. So I'll say 1 oxygen like that. And that essentially gives us 2 hydrogens, 1 oxygen like that. Each hydrogen has a mass of around 1 gram per mole. I don't know where my 1 went, y'all. I don't know where it went. There it is. Okay. I don't know why I'm messing this up. I have not used this tablet in a while. I had to go pull it out, charge it. It's been a long process. There. 1 gram per mole plus 1 times 16 grams per mole. Okay. So from the water, we're getting 18 grams per mole. And that goes with the hydrogen is just going to be, 2 grams per mole. Okay. Now, to keep it simple, since we know we're dealing with moles, right, we can just say grams and grams, right? So what I can do here is I can just skip the moles part because that part is common and then just say that for every 18 grams of water, we know we have 2 grams of hydrogen atom, okay? So that's what this is showing us here, that if you have 18 grams of water, in that 18 grams of water, we have 2 grams of hydrogen because the 16 grams come from oxygen, okay? So this is essentially the key part. This is the part that makes this question fit here because here's where you have that part 2 whole relationship, Okay. Okay, so I think we can stop here, right? Now, in the book, they kind of do a lot. Let me see if I get the same answer with this process here, because essentially I have grams here and grams here. Let us see if it works out. I really hope it works out. Let me do this. I'm trying to do better at showing you guys my screen, like the YouTube gurus. Yeah. Let me see if I can show you guys my screen. That way we can do calculations together. I need to get the calculator opened up first. Calculator. There it is. Then let me minimize my screen and then drag it over. If it will drag. There it is. Okay. So I'm multiplying the top number. Top number 1 times 3.785 times 1,000 times 2 divided by 18. Okay. I'm trying to look at these numbers. The numbers look right, but the answer looks a little bit off. I don't know. I got 420. Let's see what they got. Oops. Oh, they got 423. Oh, that's not bad, because when you multiply this out as 423, I got 420. That's not bad considering our process is a lot shorter, right? So I keep forgetting. I'm still trying to get used to this equipment, y'all. So if I do it this way, I get 420. The reason why my number is slightly more rounded up than theirs is because I kind of rounded up all my atomic masses right here. I rounded these up. But that's the answer right there, the grams of hydrogen. Okay. Once again, I use the given number, the simplest one, use my conversion factor right here. And then here's a part to whole relationship, which is what this section is all about. And then there's the answer. Okay. So let me see if I can go ahead and finish up this chapter. So this question is marked as done. We are done with this question. I can move on. The next part here is looking at empirical formula. In the empirical formula, give me just a second. Let me go ahead and pause this for a moment. Okay, we're going to pick up where we left off. The next section here is about determining the chemical formula from the experimental data. So in this section here, to quickly review what I just covered, we went from a compound or the whole, and then we got information on the parts, right? One of the parts was the percent of the part in the whole, and the whole will be the compound, the part is usually the element, right? So we did the percent by mass or percent mass of the element in the compound. That was a part to whole relationship. We did stoichiometry involving part to whole relationship. Now we're doing more calculation involving part to whole relationship. Only this time we're going from the part to the whole. So our direction is from the part to whole. So we're going from elements to compounds, okay? And this is with the determining a chemical formula from experimental data. So we're trying to figure out what the whole is, what the compound is from the elements. And the compound we're going to be building first will be called the empirical formula. So empirical formula, okay? So in this section right here, let me see. I hope my phone is not showing up because I have my phone here with me and it's just buzzing like crazy. Okay. So let me put this away so you all don't hear it. Okay. So the empirical formula, we talked about that before, is the simplest whole number ratio of the atoms in the elements, right? And so this is a step-by-step process, kind of like drawing the Lewis structure. So you start from step number 1. You will be given percentages, right, of the element. For example, carbon percent, hydrogen percent, oxygen, and you will add up all the percentages. And if they equal 100, convert the percentages to grams. So go through this step by step. You essentially, when it says convert here, there's no math in that. You just replace percentages with grams, okay? And that's after adding all the percentages and making sure they're equal to 100. The step number 2, you will convert grams to moles. There's a formula for that. To get the moles, moles are equal to grams over molar mass. Remember, molar mass is the mass you get from the periodic table. So I like to call it PT molar mass. You should just remember where it came from, okay? And then down here, once we get the moles from step 2, then step 3 will be finding the mole ratio. The mole ratio is once again, the simplest whole number relationship between the elements. So you divide the moles by the smallest number of moles possible. You will see how it plays out when I actually work this out to get the mole ratio, okay? And after that, if you end up with one of those special decimal places, you will actually multiply the decimal places, actually the whole number, the whole mole ratio, by a certain number, a certain multiplier to get a whole atom. So for number 4 here, essentially, we're told that Dalton said in his theory, atoms do not combine in parts, right? When an atom is combining, a whole atom combines. So if you get a special ratio like 0.33, 0.67, 0.50, 0.25, these are pieces of atoms, right? 0.33 will essentially be the same thing as a third. This is a third. 0.5 will be the same thing as half an atom. 0.25 will be the same thing as a quarter of an atom. So we're going to multiply these special decimal places or special ratios with a whole number to make sure we're getting a whole atom. Because Dalton said, when atoms combine, they combine in wholes. Okay? I'm going to skip over this problem for right now. I'll come back to it later on. I want to go ahead and work on one that starts with percentages. So we're starting from the beginning, like this one here. Okay? In this problem here, we're starting from the beginning. We're starting with, let me add a page here. We're starting with the percent of the elements. So let me see if I can copy this here. Can I copy this? Oh yeah, okay. So we're asked to find the empirical formula for aspirin. Let me see if I can zoom this out. Can I drag this? This is just making it worse. I'm trying to get it bigger, but it's just getting smaller. What do I do with this? Okay, apparently I don't know how to use this. Let me try it again. Okay, take this here and then drag it over there. Copy, paste, and drag it here. Oh, that's better. Okay, so I have my percent of elements, right? I'm starting with percent element. So for carbon, I have 60%. For hydrogen, I have 4.48%. For oxygen, I have 35.52%, right? And then I go from percent to grams. So you want to add these numbers. When I add these numbers real quick, it adds up to 100. So I'm just going to replace percent with grams, right? So this becomes 60 grams. This becomes 4.48 grams. This becomes 35.52 grams. And we're done with grams. The next conversion here is go from grams to moles. From grams to moles, you use the formula moles equal grams over molar mass. Okay, so the math here is going to be 60 grams divided by carbon's molar mass or atomic mass is going to be 12 grams per atom, per mole, sorry. Okay, so that should give us, I think, 5. And then we have 4.48 grams over 1 gram per mole. I'm using abbreviated numbers here. We have 4.48 moles. And then we got 35.52 divided by 16 grams per mole. And over here, let me work this out. 35.52 divided by 16. Oh, okay, hold on just a second. Somebody's at the door. Okay, I had to go pick up some pizza. Anyway, back to what I was saying. This is now 2.22. Okay. So once again, let me make sure I have everything correct. I got this right here. So the next one is going from moles to mole ratio. Mole ratio, right? So you take your moles and then you divide by the least number of moles. So I got 2.22 divided by 2.22, that makes this 1. Divide by 2.22, that makes this, hold on a second, 4.48. Can I get that? Inverse. Oh, there is no inverse function here. Inverse equal what? No. Okay, hold on. 4.48. I'm doing the math on the calculator online, the one I used earlier, 2.0. And I got 5 divided by 2.22, and that gives me 2.25. So when you're working this out, you want to get your mole ratios. If they're going to be decimal places, you want to get it to 2 decimal places, right? So you can look at that one table. So I have 1.00 here, 2.01. So here, approximate. I'm going to use the term approximate. So our ratios are 2.25. This is a special ratio because it stands for a quarter. 2.01, this is not special. So not special. And then 1.00, not special. So here's where you scroll and go to the table. And the table lists all the fractional subscripts that are special. And they put a 0 here because this first part here can be any number. All we care about is numbers after the decimal, right? So I had a 0.25, so I have to multiply all the numbers by 4 to get the quarter into a whole number, right? So going back here, I multiply this by 4, multiply by 4, multiply by 4, and I get 4, I get 8, and I get approximately 9, okay? So then the elements are going to be C9, H8, O4, right? Yeah, C9H8O4, and this is the empirical formula for aspirin, right? So you can see it, right? We started with the parts. These are all the parts. We started with the parts and use this step-by-step process to get to the whole. And the whole is the empirical formula. So hopefully you can see that. Okay. So that pretty much answers that problem here. And then if the question does ask you to get molecular formula from the empirical formula, you have your empirical formula right here. They will have to give you a way to find the value of n. N is multiplied into the empirical formula to get the molecular formula, as you can see right here. So I'm close to the end. So the easiest way to get n is you'd be given the molecular mass, also called molar mass. And then from the empirical formula, you can find the empirical formula mass, right? The empirical formula molar mass, and then solve for n. Once you have n, you multiply n into the formula, and then that gives you what you're looking for. So we should have a problem here. So let's pretend we've gone through the steps, right? To find the empirical formula C2H3O. And we're being asked to find the molecular formula. We're told here, butadiene, a main component responsible for the smell and taste of butter and cheese, contains the elements carbon, hydrogen, and oxygen. The empirical formula for butadiene, pretending we actually work to get this, and its molar mass is 86.09. So having the empirical formula and the molar mass, we have to find the molecular formula, the one that shows the actual elements present and the actual amount of each element present. So for this one here, once again, let me see if I can make this a little larger. It's hard. Okay, so I'll leave it here. So for this one here, let's see. I'll find the empirical formula mass, which would be equal to 2 carbons, each carbon is 12, plus 3 hydrogen, each hydrogen is 1, plus oxygen, each oxygen is 16, right? So let me erase that and actually put the number there. I don't know why I put the symbol. Go back. This is 16. So we end up with, this is what, 24, 3, 16, 43. Okay, so we end up with 43 grams per mole. So we need to find N. N is equal to the empirical formula mass divided by molar mass. So, oh, I think I flipped this. Sorry. Yeah, I'm kind of rushing because I have to go to the store and I'm rushing through this, so I'm a little distracted. Okay, let me focus. N is equal to the molar mass, the bigger mass, divided by the empirical formula mass. And if you mess it up, you will get a number, a value for N that is less than 1. So just in case you mess up like I just did, you will get a value of N less than 1. In that case, just flip it over to get N either equal to 1 or bigger than 1. N has to be an integer, so either 1 or above 1. It cannot be less than 1. Okay, so here, let me see. I have 86.09 grams per mole, and then divided by 43 grams per mole. So that ends up being 2. So to get our molecular formula, I'm going to continue writing down here. With N equal to, take N, multiply it into C2H3O. So we end up with 2 multiplied into C2H3O. So we get C4, right? H6O2. And that's what they got down here. C4H6O2. That's the molecular formula. And finally, the chapter ends. Okay, it was a little bit of a trial to get to the end of the chapter, but we got it done. So I hope this was helpful.